During a turbulent storm at sea, a sailor placed a dark stone onto a piece of wood and set it in a bowl of water. No matter how much the ship pitched or turned, the stone slowly rotated until it pointed in one consistent direction. This rock is lodestone, a naturally occurring magnet made of iron oxides, also known as magnetite. It takes its name from Magnesia, the ancient region where people first observed it pulling on iron objects. This rock possessed an invisible property. Without any physical tether or visible mechanism, it could reliably orient itself along a fixed north-south geographic axis. By providing a reliable heading when clouds obscured the stars, this seemingly magical force allowed early explorers to navigate open oceans. Today, we define a magnet as an object that produces an invisible pull on specific materials. You can see this selective pull in everyday life. Hold a magnet up to wood, plastic, or glass, and nothing happens. The force ignores them completely. There is a common misconception that all metals are magnetic. As this sorting visualization demonstrates, that isn't the case. Metals like copper, aluminum, and gold remain unaffected. Only specific metals, primarily iron, nickel, and cobalt, actually snap to the surface. Sorting materials by their reaction to a magnet is straightforward. But to actually use this force, we need to examine the physical laws that dictate how that invisible pull behaves. Every magnet operates using two distinct ends called poles, north and south. When opposite poles face each other, they attract and pull together. But when you flip one so that two identical poles face each other, they repel, pushing the metal away through empty space. This raises a physical question. What happens if you chop a magnet in half to try and isolate just the North Pole? When this bar magnet snaps in half, you don't get an isolated North Pole and an isolated South Pole. New poles instantly establish themselves on the broken ends, leaving you with two complete, smaller magnets. The magnetic force relies on tiny, uniform atomic structures within the metal. In a permanent magnet, all of these microscopic structures are locked into perfect alignment, pointing in the exact same direction. A magnet's power doesn't originate from its physical ends. It is the cumulative result of that unified microscopic alignment spanning the entire piece of metal. That internal alignment projects a three-dimensional zone of influence outward from the poles, known as a magnetic field. Watch as these dark iron filings rain down over a bar magnet. They immediately lock right into place, tracing out the invisible, looped pathways of the field flowing from the North Pole to the South Pole. This illustration expands that concept to a planetary scale. The Earth itself operates as a giant magnet, generating massive, invisible field lines that emerge from the geographic poles and wrap around a globe. Looking at this antique magnetic compass, the pivoting needle in the center is simply a tiny, freely suspended bar magnet. It aligns itself with the Earth's massive field lines. The exact same invisible field rules that snap two tiny desk magnets together also govern the entire planet, allowing us to navigate. Eventually, we learn to manufacture our own artificial magnets by forcing the atoms in ordinary iron into that strict alignment. The most versatile of these is the electromagnet, a device capable of generating immense magnetic pull entirely on demand. By coiling copper wire around an iron nail and running electricity through it, magnetic field loops bloom outward. But dropping, hammering, or heating a magnet scrambles its atoms. This demagnetization causes the magnetic field to vanish as the internal structure becomes chaotic. Artificial magnetism is a highly engineered state of matter. It is powerful enough to be created at will, but fragile enough that it requires proper care and storage to survive. The ability to create and control these magnetic fields at will has led to a wide range of industrial applications. In junkyards and factories, heavy industrial cranes use massive electromagnets to lift, sort, and move tons of scrap metal by simply toggling an electrical current. This aerodynamic maglev train uses magnetic repulsion to eliminate friction, allowing the vehicle to float above the track and travel at extreme speeds. Modern medicine utilizes magnetic resonance imaging, or MRI. This technology uses powerful magnetic fields to generate detailed images of the organs inside the human body. Modern engineering has mapped this invisible force, connecting the mechanics of a pocket compass to the most sophisticated technologies currently in use.